Hi, everyone. Thanks for welcoming us and thanks for coming to our talk. We're here today to tell you about our DIY electronics manufacturing journey. So in the submission for this talk, we laid out some questions that will guide us today. Why is electronic manufacturing hard? Can it be made easier and more accessible? And can we bring it back to Europe? And is there even such a thing as like the need to relocate industry? While we don't have the answer so far, we want to share with you what we figured out. So let's get started.
How we got into this. We have been making electronics and machines since about forever. Some of them you can see on this slide. Us being electrical engineers, we see issues every day that we'd like to solve with technology. And not only that, we simply love well-made products. We also want to build, protect, and anchor a future where humanity, liberty, and democracy are at the center of our lives. In this modern world, technology plays a key role in this. It's why we're here after all today. In many ways, we did not have a choice but to become engineers, but we now have a choice on how we use that skills. So now, fast forward to 2021. In 2021, my friend Andre told me about this retro gaming project called Mr. FPGA, which is based on an FPGA evaluation board. Most Mr. FPGA user setups are kind of hacky, and our desire was to provide high-quality alternatives, which is how Mr. Kiste, which you can see here, was born. Mr. Kiste is basically a fancy breakout board, which fits in a standard mini ITX enclosure. This picture shows how it looks in practice if you use it for retro computing, but it also supports all kinds of controllers. So we designed this box, and we naively thought we would just manufacture it ourselves. After all, it's just a few PCBs, it cannot be that hard. Well, as Andre knows, in a first attempt in 2022, we tried to release it, but we did not manage before running out of resources. And earlier this year, Augustine and me, we tried again, but we once more ended up putting the project on hold. Turns out that manufacturing in-house is a lot harder than we initially thought. And this is the foundation of the story we are telling today.
So electronics in boxes. So Mr. Kiste is a lead product in a category we call electronics in boxes. And we will use this product as a kind of an exemplary but real product. So it means that the design of Mr. Kiste is functional, it's capable of being CE compliant, and it follows important design for manufacturing guidelines. We've used the amazing open source software KiCad to design it. And yeah, being a real product, it offers us a basis for calculating revenue and costs, and also for production line requirements. So let's talk a bit about the product itself. So it has 3 boards per kit, and the largest board, which you can see on the right, is 17 by 17 square centimeter. Each kit has 240 components, and there are 53 unique components on the main board. On top of this, there are some challenging components to solder, such as kind of large footprint components mixed with fine pitch components, some toll and heat-sensitive parts as well. Here you can see the actual main board of Mr. Kiste staged on our pick-and-place machine. Overall, the design is quite complex. But our idea is that if we can produce this in-house, we can pretty much produce any product, any electronics in boxes type of product we want. But before we move on to all the cool technical stuff, let's take a step back and ask ourselves an important question. Why even attempt this?
Earlier this year, we gave a previous version of this talk at KeyCon Europe, and were asked why we didn't simply send our files to JLC PCB, which is a popular and very affordable Chinese contract manufacturer. Working with such manufacturers is popular for this kind of small-scale projects for very good reasons, which I will illustrate with a story. A friend of Augustine goes to Chinese companies to get his open source product produced and distributed, and he said, quote, "The benefit of doing it in China is that they are just so much faster and resolve issues in an instant. It's just a pleasure to work with them. From a personal perspective, I'd love to keep it in Europe. But if I have to wait for 2 weeks for an answer from a supplier, I just order my things in China instead. Happened to me several times." The last quote for an SMT was 2,300 euro net in Germany, plus 2 weeks no answer, plus 6 weeks estimated for manufacturing, plus I had to source the parts myself, ordered in China for 150 euros, end quote. Having worked in electronics many years, we can confirm this quote is quite to the point. It really seems like European contract manufacturers are either not interested or incapable of doing this kind of business somehow. Faced with these and many more difficulties, we simply can't accept that things are this way. We strongly believe we could do it better ourselves, which brings us to the next reason we are doing this. We are stubborn. We simply can't accept that European electronics manufacturing is like this and that no one seems to want to do anything about it. We know how to build machines. A production line is like any other project, right? Or so we thought. This is where we get to what we call myths of manufacturing.
Okay, so we'll share some myths, what we call myths of manufacturing with you. So the first one is pay some money and get a factory. And so part of the conventional wisdom is that manufacturing is expensive and it's gated by capital expense. After all, we all know that if you invest a few billions, anyone can open a semiconductor factories, right? Of course, in practice, to do so, you need to know which brand of wall paint won't ruin your process or which chairs won't have like this specific heavy metal contamination that will cause electromigration and completely destroy your transistors. This is process knowledge. The only way to get process knowledge is to do production yourself or to pay someone a lot of money who has done so before. So manufacturers in Europe seem to be sitting on this knowledge and they just do what they already know and maybe they sprinkle in some AI in it, but not much more. They serve big OEMs or smaller companies which seem to have kind of lost their sense for how long it takes to do things and how much it costs to manufacture electronic assemblies. And this is a strength China has. Many small players figured it out on their own, and they all share the results and the knowledge. They all collaborate. And yeah, we laughed at how badly soldered and wrongly assembled their products were for years. Well, who's laughing now? So myth number 2, a small scale is not profitable. So we took our Mr. Kiste product very far, very close to actual manufacture. And here's the data we have. So our net price will be 147 euro. Our cost of goods sold is 84 euros, which is 50 euros of materials and 34 euros of labor costs. And this leads to a gross profit per kit of about 63 euros. So gross profit does not cover distribution or packaging or operating costs, for example, but these numbers leave sufficient margin. And overall, looking at it, is it working now again? Oh.
Hello?
Overall,
is that working?
Yeah. We are having an issue. Oh, it's good? Okay. Overall, we're looking at a typical cost structure for an electronics product. It's not working. Oh, I think it works again, right? Can someone do this? Good, thank you very much. Where was I? Gross profit does not cover distribution or operating costs. But yeah, the cost structure of this product we think is kind of typical for an electronics product, so it should work out. So based on our worst case throughput for the production line we will discuss today, of 1 kit per hour, we could manufacture 240 units a month, and the revenues from selling these kits would be enough to sustain 2 employees. Of course, sales take time to ramp up, and we expect to sell kind of a mix of smaller products at first instead of just a single complex one, etc. But we think it will work out. So myth number 3, you need expensive tool to do production. So how is it even possible to do, to develop all the needed processes without buying expensive tools? So first, basic production does not require the latest and greatest tools. Second, open source and open hardware are real game changers, and we can basically build our own tools, and we can avoid reinventing the wheel and benefiting from the division of labor. That's kind of the idea of open source. We can integrate these tools in whatever toolchain we want, and it allows us to do what was previously only exclusive to enterprise solutions. These open source tools did not exist 20 years ago, and they're really key enablers to our technology. So if it's possible, then why is nobody doing it? So first, it's very hard. It requires a lot of electronics knowledge and industry experience and more. And second, investors are not interested in what they perceive as kind of an antiquated business model, manufacturing, especially with how it's perceived right now as a struggling sector in the press. They typically also don't like investing in smaller projects. They would rather, for example, invest 10 million in one project than like 1 million in 10 projects. Finally, what we do actually takes time to scale because you actually have to ship real-life product to real-life customers, and these products have to be valuable to them. And this is like to be compared with more attractive digital products which can be instantly scaled. How much does it cost to build a production line as cheap as we could make it? At this point, we have the physical space and basic equipment in place to produce a product like Mr. Kiste, and this cost around 35,000 euros, which relatively speaking is not that much. This does not take into account our cost of living, which we fund through doing freelance work and consulting on the side. By the way, we're available for hire. So far, we've worked about 6 months on the production line after spending about a year setting up the very foundation of the company and of the infrastructure. We're not done proving this is possible, but we strongly believe we're basically 50% done. So now that we have this out of the way, we can finally discuss the really cool machines we bought.
Okay, thanks. Before we start, though, let's briefly talk about what SMT even is. SMT stands for Surface Mount Technology. It is how almost all modern electronic products are made. As you can see on the slide on the left, SMT components have no leads that go through holes in the board, as it was done in the past with through-hole technology. You can see it on the right. Instead, they just sit flat on top of it. In SMT, you print something called solder paste, a metallic paste, through a stencil onto specific areas of the bare circuit board. Then you place the electronic components on the board. After placing the components, you then solder them to the board in a special oven, which melts the solder paste. This connects the components both electrically and mechanically to the board, and you can kind of see it well there in the picture too. Okay, so in this diagram you can see that the 3 steps mentioned before, stencil printing, pick and place, and reflow soldering, are just a small part of the basic production process of an electronics product. And even beyond this diagram, there are actually many more elements to take into account. Today we will only talk about the first 3 steps, though, as they cover the most ground in manufacturing a modern electronics product. And on top, they are basically automatic and very low in labor.
So first I'll tell you about stencil printing. So on the right you can see the actual Mr. Kiste PCB, one of them that we've printed with paste, and this is like an okay-ish result. Perfect printing means that soldering results are great and there's no need to rework. What's up? Oh, do I need to speak? Oh, okay. So perfect printing means good soldering results and very little need to rework. What matters is that printing one board is not a process. You need high repeatability and high reliability. For example, you need to tightly control the temperature of the paste and even the room temperature, and you cannot use paste past its best before date. For the squeegee that spreads the paste, angle, pressure, and speed are very important parameters as well. The stencil needs to be tensioned and supported properly, and the lift-off speed of the stencil needs to be controlled. So the tool we got to do this is a manual stencil printer for from a second-hand SMT parts dealer. These printers can be bought second-hand for 1,000 to 2,000 euros. This one is about 1 by 1 meter in size, and it can accommodate production-sized stencils. Such stencils are very large because you are actually kind of rolling a paste roll back and forth to do like 1 PCB on the front stroke and 1 PCB on the back stroke to like kind of make the process more efficient. And if you ever wondered why the JLC PCB stencils are so big, it's because they're supposed to fit in this kind of printers. So while some of the process variables can be dialed in like the machine itself, there's still kind of a field to acquire to learn the process of printing with this machine. So what did we learn? We learned that even for a tool as simple as this one, if you buy it used, it's going to bring pain. We had to clean it, we had to actually design and create our own squeegees for it, we had to replace broken parts and many other things. It also requires compressed air to work, which we had to install in our workshop, and that's additional time and expense to set this tool up. But with quite a bit of experimentation and work, we managed to get really good results, and now it remains to be seen how it will handle an actual small-scale series production run.
Okay, after stencil printing comes pick and place, and this is really the fun part. Of course, we mean the painful kind of fun. While other process steps require only relatively simple machines and are pretty straightforward, pick and place is much more complex. So, what do we do? Well, it worked well for the stencil printer. In the case of pick and place, just buying a used machine is not so easy. Sure, you can buy one for 5 to 15K that can then place around 2,000 to 20,000 components per hour, depending on what you buy. The issue, though, is that spare parts and service will both be required at the worst times and that they will be subject to questionable availability at high cost. Let's not even talk about the software, except maybe if you're a Windows XP fan. Another small but kind of relevant issue is that these machines typically do not fit through our front door because we have kind of limited space. So what do we do? Opulo, a US-based company, released their open source LumenPnP v4 in 2024. It checks many boxes of what a proper machine should be. It costs about 1,800 euros without feeders and can place between 950 and 1,580 components per hour. And this Opulo machine solves a lot of foundational problems of pick and place for us. It gives us a machine frame, does motion and vision, and has 2 pickup heads. And most importantly, it is open, hackable, and extensible. But that machine would be pretty useless without software, and this is where Open Pick and Place comes into the picture. Open Pick and Place is the most popular and pretty much only open source pick and place software. It allows you to load board and part data, and it executes placement jobs and uses machine vision to inspect boards and parts. OpenPnP is adaptable to pretty much every machine type, and Opulo offers a ready-made machine profile for OpenPnP. All of that being said, again, pick and place is a very complex topic. What we showed you so far are the basics, the theory. When we talk about practice, there is a lot more to consider. Most importantly, we cannot talk about pick and place without looking at components, because the sole purpose of a pick and place machine is, well, to pick and to place components. Components can come in all shapes and sizes, and you typically need to load many different components onto your machine. The hard drive PCB depicted on the right shows this variety, and actually it's a very sensible PCB. The components are not even close to the really odd ones. And the picture on the bottom left shows the smallest and largest component we have on our Mr. Kester board, and you can see that this is quite a big difference in size. This variety matters so much because you don't just buy a pick-and-place machine and are done with it. You need to configure the machine components, set up machine vision pipelines, and so on. And before we continue, let's look at the way most components are packaged in so-called tape and reel. Essentially, you get a reel of plastic or paper tape, and that tape has many small pockets in it. In every pocket, there is a component, and depending on the size of the component, the tapes can come in varying widths. While this is an 8mm tape, they can be up to 200mm wide. So, how do you get the components out of this tape and onto the PCB? That's where so-called feeders come into play. Feeders get loaded with the component tape and dispense the components contained in it one by one. For each component type, you need a suitable feeder. For the main board of Mr. Kiste, that means we need 53 feeders, which is quite a high number. And each feeder has to reliably advance the tape thousands of times without ripping the carrier tape or cover foil, without the components jumping out of the pocket in the tape, and with very high positional accuracy. Unfortunately, the reliability of the machine is divided by its number of feeders. A single feeder failure means that the component cannot be placed, thus requiring human intervention. In the end, any machine is as flexible as its feeder capacity, types, and configurations. Being able to easily change the feeder configuration is extremely important to small series manufacturing. Going back to the Lumen machine, Opulo offers feeders in 8 and 12mm widths. They are one of the very few commercially available open source feeders, and that alone is a huge achievement. Unfortunately, we also need feeders for 16, 24, 32, 44, and 56mm tapes. And also, we'd have to pay 4,500 euros for those 60 feeders we roughly need, which is 75 euros per lane. Quite a steep price, given we don't know how reliable they really are, and if they last, and if they are in the end a sound investment of capital. So what did we do instead? Germany is Siemens land, and Siemens makes feeders. Our research has shown that Siemens S-series feeders, also called Schulz feeders, are widely available. They are deprecated but still used in the industry, and we estimate hundreds of thousands in Germany alone, having been manufactured for over 20 years. They cost about 10 euros per 8mm lane. This is one with 2 8mm lanes. If you negotiate moderately well, which is really quite a crazy value for the money. That being said, we now have a pile of them. You may ask, isn't this the same issue as buying an old pick-and-place machine? I would answer not quite, because the issues with used machines are everywhere, in software, in motion and vision, and so on. And these are issues that OpenPnP and Opulo solve amazingly well, and open source. The feeders, on the other hand, are relatively straightforward and narrowly scoped components of a pick-and-place machine. In this picture, you can see these feeders come in many different widths. With the 3x8mm feeder, you can fit over 80 different component types on the OpenPnP machine. And what's more, they are extremely reliable. We've read EEPROMs from some of our feeders, and some of them have over 30 million picks and still work reliably. So, how does it work with OpenPnP? Thanks to people like Bill Ruckman and Bernd Walter from the OpenPnP user groups who have reverse engineered these feeders, we also know they have a relatively simple UART interface. These people also have developed a feeder integration in OpenPick-and-Place to control these feeders through an Arduino-based custom G-code interface. This interface you can see in the picture. Unfortunately, in practice, we noticed reliability issues such as glitches and timeouts, and also the controller turned out to work only with Gen 1 feeders, while all feeders wider than 8mm are actually so-called Gen 2 feeders. In the end, we had to completely rewrite the controller firmware to fix the glitches and support the Gen 2 feeders. Also, we now have full diagnostic coverage by relaying all error codes to OpenPick-and-Place. On top, we are using previously unused EEPROM sections of the feeders to store a unique ID and the feeder type in each feeder. This opens up a whole new world of integration options, such as feeder-specific offset data and integration into a future feeder inventory management system. With the basic communication being sorted, we then felt confident to double down on our concept and to integrate these feeders properly with the LumenPnP machine, which you can see on this picture. And the feeders go on the left and the right in some feeder banks. What still needs to be done is to improve the OpenPnP GUI and workflow with the feeders. On this slide, you can see a mock-up of our desired feeder wizard target state, and this is needed because right now it's easy to enter data and then not correctly apply it to the loaded feeder, kind of Therac 25 style for those of you who know. While used Siemens feeders are not a forever solution, they are good enough for now to move us forward on our journey for local small series manufacturing. That being said, to use OpenPnP in a production scenario, we've identified a number of additional aspects that need some work. One of them is that currently components loaded into feeders are stored in the machine config, which is an XML file stored locally on the computer that runs OpenPnP. This means that feeders cannot be used across multiple machines because the config is local to one machine. We want to implement an SQL database provider so that multiple machines can access the feeder data. Another thing is that right now, when you press a certain button, the nozzle just crashes into the feeder shutter. And to fix this, we basically need to completely refactor the pick cycle logic because shutter feeder support was only added on top in OpenPnP. It's these things that take a lot of time to do properly. To wrap up this section, we prepared a brief video of how it looks in practice as of now. And it doesn't work, it seems. Oh?
Yes. Okay, it needs to buffer a bit. So the part does vision to check alignment and then puts it down.
Yeah. Okay.
Thank you.
Thanks.
Thank you.
So at this point, we printed solder paste onto the board and placed components on it with the pick-and-place machine. And what comes next is?
Yes, next comes reflow soldering. So we need to actually solder the components to the board. And to do this, we need a reflow oven. So a popular choice for reflow ovens are DIY modified toaster ovens. And this was not an option for us because we want to be able to solder boards for 8 hours a day without breaks, basically, and reliably and safely as well. In series manufacturing, you would typically use a conveyor oven, but these are too large for our space, and if they are compact, they have very steep thermal gradient, and this can damage the boards. Instead, we bought a production batch oven, which you can see in the picture. Well, batch ovens are often meant to be used for prototyping. There are some you can use for series production. This one we got can heat through air convection, which is very uniform, and it does not damage components. It also has automatic forced cooling, which means that it does not need human intervention to cool down, and on top it has very good humid traction. Trying to buy one shows that nobody wants to sell them because they're just too useful. You can just plug it in the wall. You need like a 30 amp single pole outlet, high vacuum flow, like a high vacuum flow extraction, and like a high flow fume extraction, and compressed air cooling, and a few other things. And this took like months, unlike weeks, to set up. And an oven is still not a process. You can't just like put a board in it and solder. So we had to create a working process, and we did the trials with a data logger, which you can see on the slide, with like multiple probing points on the PCB to study how the profile happens. And through this trial, we managed to get the reflow profile about right. And once again, we have to see how it works in series production, but we're quite confident. So with the stencil printers, the pick and place, and the oven taken care of, we have the core technology to manufacture a board. But there's one more aspect we need to discuss, which is integrated manufacturing.
So while the previous slides focused on domain-specific manufacturing technology, there is also a more general perspective on being a manufacturing company. Gene Kim from the Phoenix Project said that, quote, every company is a technology company regardless of what business they think they're in. A bank is just a IT company with a banking license. For us, this means that we cannot just focus on the physical process steps, but that we also need to have a concept to integrate them digitally. For manufacturing, management of data is a critical element at design time, during production, and even after an electronics assembly has been built. We will explain only briefly how we plan to do it, as our implementation of this part of the project is only very basic so far. With the tools we presented and some other tools we did not talk about, we strive to have complete control of our data throughout the entire product lifecycle. We use Keyboard to generate all the required data from our keycard design. Board data and stencil data then go to our board fab of choice. Placement data is used by our OpenPnP setup, and the BOM is imported to inventory for material logistics and production planning. OpenPnP also accesses inventory to populate its database of parts that can be loaded into feeders and assembled onto a board. Further custom scripts integrate inventory with our accounting software so we can track the value of our stock accurately. Beyond, what's not even in this diagram is all our server infrastructure, which is based on open source too. Things like Proxmox and Linux are simply critical enablers of our work. For us, being able to create an integrated manufacturing system like this is possible because of the power of open source software.
So let's try to conclude on this. First, we've open sourced so far as much of our work as we could open source. So this includes this new V2 feeder controller hardware and firmware, as well as the feeder reverse engineering documentation we wrote, and a comprehensive 2x8 feeder overhaul guide, which explained to you how to tune the feeders and disassemble and assemble them. Next, considering everything we've said so far, where do we stand? So as mentioned before, we consider this project to be halfway there. Our goal is to finish what we started and set up a fully functional open source based electronic production line. And we are exploring various ways to do this while also making sure we can still pay our rent. It's likely that our next step is to design and manufacture a rather simple product and to sell it. And that means basically one PCB, 30 components maximum, 15 component types maximum. And that we want to do that to demonstrate the end-to-end viability of our process. Ultimately, we still want to manufacture 100 Mr. Kister boards out of spite. And even if we might be too late for the market, and just because we can, and because we're stubborn.
So, to conclude, manufacturing is hard, but I think we all got that by now. What's more important is that there's nothing mystical about it. You can just learn to do it and do it well. Hardware does not magically show up at MediaMarkt or Micro Center, and most of our hardware we import from China. There's nothing wrong with that in many ways, but we'd like to learn to do what these Chinese companies can do here in Europe, in part because our existing companies seem unable to do it. Maybe European companies got too comfortable sitting on their past or present wealth and forgot how much things are truly supposed to cost. Local manufacturing is a...
Yeah, thank you.
Thank you.
We have a lot of things to say, so it's a bit difficult to pause for applause, but thank you very much for your attention.
Local manufacturing is a valid investment, but you need to actively choose it over hype technologies. We want people to reproduce what we've done, and we want to see more small companies doing this. At this point, we're looking for people to join us our journey, including figuring ways out of for collaboration. In a society that runs on technology, manufacturing basic electronic systems that keep our lights on and our water flowing is a critical capability, and we should not forget about how to do this.
Thank you. Yeah, thank you. If you want to discuss this with us or have questions, you can find us after this talk at the Cyberraum assembly, which is linked in this QR code. That will take you to the C3 nav. You can also check our GitHub and sign up for our mailing list on our website, and yeah, many other things. Thank you very much.
And thanks to the organizers who made this great event possible.
And thanks to the translators for translating this talk in French. Merci beaucoup.
Wow. Amazing talk and an amazing speed. Great work, guys.
Thanks.
Thank you so much, Henning.
I guess, yes, quite some questions. Great. We'll start with microphone number 5, please.
Hello. That's a great idea with used Siemens feeders, but I think you forgot one thing. That's humidity of the components. Because for a reliable production, you need a controlled humidity, even of the smallest components, of the passive components, because you face otherwise cracking, which leads to very nasty failures and not so long-lasting products.
Can I answer this one, Alex?
Sure.
Yes, this is something we didn't get into today because it's kind of a detail, but we have an MSL management concept, which hasn't been tested yet, but we have one.
So yeah, we were thinking about this topic, and we also need to see if we can optimize the feeders for quick loading, unloading of components, so that we can put them into dry storage and out of dry storage again, but it's on our list.
Yeah, there are many aspects that we have to work on. We also have a concept for ESD and other elements.
Thank you.
Okay.
Yes, thank you for your question.
Question number 3.
Thank you for this important and incredibly critical work. Thank you very much. If you will ever enter the freelance market where we can order PCBs from you, when approximately and how can we contact you?
Thank you. That's a
Thank you so much.
very interesting point, because we would probably never want to be a traditional contract manufacturer, because we believe that when we convince people who design things to kind of buy into, but it's open source, so it's not actually buy in really into a standard workflow, then we would be able to much more effectively work with them, because it's a back and forth of production data, communication, and so on. So this is kind of a bit of a different philosophy where you don't, where basically the process itself is open source, and you can,
I mean, we would consider probably working with people and being like looped in the actual design process. Thank you for your question.
Microphone number 4, please.
Hi, thank you for the talk. How involved are you with the OpenPnP community? Because there's a lot of work in feeders right now, so some of the problems you talked about are already being tackled. Are you aware of that?
I was not aware of this, but I have contacted Jason von Nida, the main maintainer, I assume, but we haven't yet heard back from him.
Yeah, you might want to talk with Toby about that. He's more active.
And maybe some small addition, like this is basically 6 months ago we worked the last time on this, because we have other priorities now, so we can't unfortunately be in touch all the time, but we will follow up. It's a very good suggestion. Thank you.
Yes, thank you.
Microphone number 2, please.
Oh, thank you for your interesting take on this. I was thinking about continuity. How would you describe your plan for what if you would both fall ill or hit a bus, only have a concussion, but still? Do you already train people, or where do you store your knowledge? Where do you disperse your knowledge? That's my question.
Thanks for that question. I think we would like it to not be about us, basically. That's why we open sourced as much as we could now, and that includes, for example, this overhaul documentation of the feeders. I think it's over 100 pictures, and like it's a really long guide, and also the firmware and the reverse engineering notes and so on. So I think the best that could happen is that others join us on this mission, and we open source as much as we can of this, and basically the process knowledge lives on in as many people as possible, so we can actually manufacture electronics here.
Yeah, so just to add to this, I forgot what I want to say. Yes. So we are very much closer to the start of the journey than to the end on this. We are, that's the first time we're basically talking at a major conference about this project, and we're really open to working with others, but we would have to, for example, also figure out the ways of collaboration. So as Alex said, there's a lot of information now that we open sourced. I think the feeder overhaul guide is amazing because it's very detailed pictures of the feeders that were never before seen basically online. But yeah, this is really early work for now. And thank you for your question.
Microphone number 1, please.
Hi. First of all, thank you for your talk. It was very interesting. I was wondering, you talked about everything kind of that happens after you have a PCB made. I assume your PCBs still get manufactured in China, and do you have thoughts on kind of taking that step as well and figuring out how to do even more of this manufacturing process?
I think I can safely say we will never manufacture PCB in-house. It's like a crazy chemical process and everything. But we can get PCBs manufactured in Germany, actually. It's not that much more expensive than China, actually. And it's very nice because you can actually walk through the factories, you can visit them, see issues, talk to people, a bit easier.
I understand the question, and we were wondering about this for very much time and very often, but we've got to start somewhere, basically. That's our perspective that we take. But yeah, we would like to do this, but yeah, okay, thank you.
Yeah, thank you for your question.
Thank you. Just like as one follow-up, it surprises me slightly that you say like the German companies are perfectly happy manufacturing PCBs at a somewhat competitive price, but then the step after that they completely seem to fail on.
Well, the complexity with SMT assembly really is you have to manage so many components of such variety and place them accurately and solder them well and everything, and that's really the most, in a way, it becomes the most expensive part of the process.
Let me look at the time. I want to, can I, just very briefly, the complexity is not exactly in the technology, it's in the organization, and very big part, because what you do is you email Excel sheets back and forth, then you have them on the phone, then there are some changes that are not tracked in the design, and then you need to, I don't know, do another revision on short notice, and it gets a terrible mess. And this is what we want to work on also, because open source enables us to integrate the data flows in different ways and to make this process more efficient and more fail-safe. Thank you.
2 questions left. One from microphone 3, please.
Yeah, thank you for your nice talk. I have one question regarding your first answer called about the ESD problem and in general the material handling. Do you have any plan for this, or it's just manual picking up the product from one step and then bringing it to the next process step?
So we have an ESD concept. We're basically fully equipped with ESD tables and chairs, and as far as we know, our flooring is quite ESD friendly, and we can handle everything with gloves and protocol and everything. And I guess the part of this we would open source would be protocols for handling, for safely handling electronics.
And there are open source conveyor thingies and so on also in the works by other people, and that's what we would look to integrate with, but first it needs to work at all.
Oh yeah, if your question was about full automation, right now we are going to be carrying things between machines, definitely, yeah.
Okay, thank you.
It's actually more efficient than one would think in terms of revenue.
Thanks.
Okay, last question, microphone number 5, please, a short one.
Hello, do you have any plans on open sourcing end-of-line manufacturing tests like with test beds, or are you aware of any project which tackles this?
There are a few projects that give you like open source test devices and a framework for them, so you can ship them to a Chinese contract manufacturer typically, and they download their test instructions from servers on the internet. So the Chinese people, the manufacturers just get a box, they put the PCB on, and the test runs automatically. This is partially open source. We have not done much in this direction yet, but of course we would like to.
We would like to, and I would like to add as well that it's a bit difficult with test setups because they're always highly customized to the product, so it's a bit kind of an endless battle to create a project that can adapt to every kind of product that's imaginable, but yeah. Thank you for your question.
Thank you.
Augustine, Alex, great talk. Many thanks for it. Guys, please give them a warm applause.
Thank you so much.
Thank you.
Thank you so much, Henry. You're the best moderator.